Hello and welcome. In this notebook, we will start with SQL basics, learning what SQL is and why it matters. We will cover essential commands like select, from, where, order by, limit, and working with aliases, math, and strings. Next, we will explore filtering, aggregation, and grouping. You will learn distinct, group by, having, and common aggregate functions like count, sum, average, minimum, and maximum. Then we move to joining multiple tables using foreign keys. We will practice inner joins, left joins, right joins, full outer joins, self joins, and cross joins. In the next section, we focus on subqueries and set operations, including in, not in, exists, and combining results with union, intersect, and except. We will also cover data modification and table design. This includes insert, update, delete, creating and altering tables, data types and constraints such as primary key, foreign key, and not null. Advanced SQL topics include window functions, case expressions, common table expressions, views, and indexes for performance. Finally, we will look at SQL in the workplace, from building reports and dashboards to connecting SQL with tools, working with different databases, optimizing queries, managing permissions, and version controlling SQL scripts with Git. If you like this course, please consider like and subscribe. SQL Basics, the foundations. What is SQL and why it is important? SQL, which stands for Structured Query Language, is the standard language used to work with relational databases. When we say relational database, we mean a database where data is stored in tables with rows and columns, and these tables can have relationships between them. SQL allows us to create new databases and tables, insert new data, read existing data, update records, and delete information when needed. These are often called the CRUD operations: create, read, update, and delete. One of the main reasons SQL is so important is that it is used across almost every major database system, including MySQL, PostgreSQL, Microsoft SQL Server, Oracle, and SQLite. This makes SQL skills highly transferable. If you learn SQL for one database, the core concepts will work in another with only minor differences. For software developers, SQL is essential because almost every business application depends on storing and retrieving information, whether that's user accounts, product inventories, transactions, or analytics data. In short, SQL is the bridge between your application and the data it needs to function. Mastering it will make you far more effective in any software development role. Select, from. The select and from keywords are the foundation of almost every SQL query. Select tells the database which columns you want to retrieve. These could be one column, multiple columns, or all columns in a table. When you want all columns, you can use an asterisk, which is the symbol for everything in SQL. From tells the database which table to retrieve the data from. The general format is select, then the column names, then from, followed by the table name. For example, if you have a table called employees and you want to get only their first names and last names, you would use select first name, last name from employees. If you want all details for every employee, you would write select star from employees. Remember, select decides what data to show, and from decides where to get it. This pattern will repeat in almost every query you write. In this example, we have a table named Employees with columns for ID, first name, last name, department, and salary. The first query shows how to select only the first name and last name columns. The database returns two columns, first name and last name, with the matching values for each row. The second query uses select star, which means select all columns. The result shows every column in the table, including ID, department, and salary. By comparing the two outputs, you can see how select controls exactly which data is returned. Where clause. The where clause is used to filter rows based on specific conditions. Without a where clause, a select statement returns every row from the table. But in most cases, you only want rows that meet certain criteria. The condition after where can use comparison operators. You can combine multiple conditions with the AND keyword. AND means both conditions must be true for the row to be included. You can use the OR keyword when you want rows that match either one condition or another. The NOT keyword reverses a condition. For example, NOT department equals sales will match all departments except sales. In real applications, where is how you target the exact data you need instead of working with the entire table. Let's walk through these 5 queries step by step. In the first query, we select first name and last name from the employees table, but only where the department column equals the value IT. This filters the rows so that only Jane Doe appears, because she is the only one in the IT department. In the second query, we select first name and salary, but only where the salary is greater than $55,000. The greater than sign compares numbers, and only Jane meets this condition with a salary of $60,000. In the third query, we combine conditions with the AND keyword. Here, the department must be IT, and the salary must be greater than $55,000. Both conditions must be true for the row to be included. Jane meets both conditions, so she appears in the result. In the fourth query, we use the OR keyword. This means the row will be included if either condition is true. We want employees from IT or HR, so the result includes Jane from IT and Mark from HR. Finally, in the fifth query, we use the NOT keyword to reverse the condition. This returns every employee whose department is not sales. That removes John from sales and keeps Jane from IT and Mark from HR. Order by ascending, descending. The order by clause is used to sort the rows returned by your query. By default, SQL sorts in ascending order, which means numbers go from smallest to largest, and text goes from A to Z. If you want descending order, you add the DESC keyword after the column name. In descending order, numbers go from largest to smallest, and text goes from Z to A. You can sort by more than one column. For example, you could sort by department first, and then by salary within each department. Order by is often used together with where, so you can first filter the data, and then sort it in the order you need. Sorting is especially important when you want to find top values, bottom values, or display data in a meaningful sequence. In the first query, we sort the results by salary in ascending order. We explicitly wrote ASC, but it is the default, so you could leave it out. This puts John at the top with 50,000, followed by Mark with 55,000, and Jane with 60,000. In the second query, we sort the salaries in descending order by adding the DESC keyword. Now Jane is first with 60,000, Mark is second with 55,000, and John is last with 50,000. In the third query, we sort by 2 columns. First, we sort by department in ascending order, so the departments appear alphabetically: HR, IT, and sales. Then, within each department, we sort by salary in descending order, so the highest paid person in each department appears first. This is useful when you need more control over how your results are organized. Limit or top in MS SQL. Limit and top let you ask for only a few rows instead of the full table. Limit is used in MySQL and PostgreSQL. Top is used in Microsoft SQL Server. Offset skips a number of rows and is useful for paging results. Always use order by before limit or top to make the result predictable. If you omit order by, the database can return rows in any order. When you need the top n items, sort first and then limit the result. First example. We select first name and salary. We order by salary in descending order. Then we apply limit 2. That returns the 2 highest salaries. The output shows Jane with 60,000 and Mark with 55,000. Second example. We order by salary in descending order. Then we use limit 1 offset 1. Offset 1 skips the highest row, and limit 1 returns exactly 1 row after the skip. The result is Mark with 55,000, which is the second highest salary. Third example. We use limit 2 without an order by clause. This returns 2 rows from the table, usually in insertion order. In our sample table, that gives John with 50,000 and Jane with 60,000. Important note, without order by, the database may return rows in a different order on another system. For predictable top or bottom results, always use order by. Fourth example. This is Microsoft SQL Server syntax using top 2. We select first name and salary and order by salary descending. Top 2 returns the top 2 rows after sorting. The output shows Jane with 60,000 and Mark with 55,000. Fifth example. This query shows the SQL Server pagination pattern using offset and fetch. Pagination means breaking large results into smaller chunks, called pages, so the user can see part of the data at a time instead of loading everything at once. For example, a web page might show only 10 results per page, with a next button to see more. In this example, we order the results by salary in descending order. Offset 0 rows means we start from the first row in the sorted list. Fetch next 2 rows only means we take exactly 2 rows after the offset. This gives the top 2 salaries, the same result as using top 2. Important beginner tips. Offset always starts counting at 0. Limit, top, or offset fetch should always be used with order by to control which rows appear. Without order by, the rows you get may change between queries. For large tables, pagination queries work faster when the column you use in order by is indexed. Aliases with as. The as keyword in SQL is used to create an alias, which means a temporary name, for a column or a table. A column alias is useful when the original column name is long, unclear, or when you want to make the result easier to read. For example, if your column is called first_name, you can alias it to just first name in the output. A table alias is helpful when the table name is long or when you are working with multiple tables. It lets you refer to the table by a short nickname inside your query. Aliases only exist while the query is running. They do not rename the actual column or table in the database. This feature is especially useful in reports, dashboards, and when joining multiple tables, because it makes your SQL code shorter and the results more user-friendly. First example, we select the first_name column and alias it as first name using the as keyword. The same is done for last_name, aliased as last name. In the output, the column headers show the new names. This is useful when displaying results to users who may not be familiar with database naming conventions. Second example, we again alias first_name as first name. For the second column, we multiply the monthly salary by 12 to get the annual salary and alias the result as annual salary. This way, the output clearly shows the calculation result with a meaningful label. Aliases are especially helpful for calculated columns because otherwise the column header might just show the formula. Third example. Here we give the employees table a table alias of E by writing employees as E. This allows us to refer to the table as E in the rest of the query. In the order by clause, we use E.salary instead of writing employees.salary. Table aliases are very useful when working with multiple tables as they make queries shorter and easier to read. In fifth example, select E, first name, E salary, uses the alias E for the employees table to qualify the column names. While it's unnecessary in this simple query, it's considered a best practice. Explicitly naming the table or its alias makes the code clearer and prevents ambiguity, especially when a query involves multiple tables that might share column names. Basic math and string operations. SQL lets you perform basic math and string operations directly in your queries. Math operators include plus for addition, minus for subtraction, star for multiplication, slash for division, and percent for modulo, which returns the remainder after division. You can use these operators in the select statement to create calculated columns. For example, multiplying a monthly salary by 12 to get an annual salary. For working with text or strings, you can combine values using concatenation. In PostgreSQL and SQLite, this is done with a double vertical bar. In Microsoft SQL Server, you can use the plus sign. In MySQL and most databases, you can use the concat function for consistent results. Combining math and string operations with aliases makes query results easier to understand and ready for reporting. First example. We select the first underscore name and multiply the salary column by 12. This gives the annual salary, which we alias as annual salary. The output shows monthly salaries converted to yearly amounts: $600,000 for John, $720,000 for Jane, and $660,000 for Mark. Second example, we add $5,000 to each salary using the plus operator. This simulates adding a fixed bonus to each employee's pay. The result is aliased as salary with bonus. John's new total is $55,000. Jane's is $65,000, and Mark's is $60,000. Third example, we join the first name and last name columns into a single column called full name. In PostgreSQL and SQLite, this is done using a double vertical bar between each part. We also include a space in quotes between the first name and last name so they are not stuck together. The output is John Smith, Jane Doe, and Mark Brown fourth. Example, this shows the MySQL way of doing the same thing using the concat function. Concat takes each part as a separate argument and joins them together. We again include a space between the names. The output matches the previous example. This method works in most databases and is safer when you want your SQL to be portable across different systems. Third example, we join the first name and last name columns into a single column called full name. In PostgreSQL and SQLite, this is done using a double vertical bar between each part. We also include a space in quotes between the first name and last name so they are not stuck together. The output is John Smith, Jane Doe, and Mark Brown. Fourth example, this shows the MySQL way of doing the same thing using the concat function. Concat takes each part as a separate argument and joins them together. We again include a space between the names. The output matches the previous example. This method works in most databases and is safer when you want your SQL to be portable across different systems. Filtering, aggregation, and grouping. Distinct. The distinct keyword in SQL removes duplicate rows from your query results. When you select a single column with distinct, it returns each unique value only once. If you use distinct with more than one column, SQL will treat each combination of column values as a unique record. That means two rows with the same department but different salaries will be considered different. Distinct is often combined with count to find how many unique values exist in a column. For example, counting distinct departments in a company. Beginner tip: use distinct carefully on large tables, as it requires SQL to scan and compare rows to find duplicates. If you need predictable ordering, always pair it with order by. First example. We select only the department column and apply distinct. This removes duplicates, leaving each department name once: HR, IT, and sales. Second example. Here we apply distinct to both department and salary. Now uniqueness is determined by the combination of those columns. HR appears twice because the salaries are different. Third example. We count the number of unique departments by combining count with distinct. The output is 3, meaning our company has 3 departments in total. Group by and having. The group by clause in SQL groups rows that share the same values in one or more columns. Once grouped, you can apply aggregate functions like count, sum, or AVG to get summarized results for each group. Where filters individual rows before grouping, the having clause filters the groups after the aggregation is done. This is the key difference between the two. You can group by more than one column, which creates subgroups based on the combination of those values. Always remember that group by comes after where and before order by in a query structure. First example. We select the department column and calculate the average salary for each department using the AVG function. We alias the result as average salary so the output is clear. The group by department clause means that all employees with the same department name are grouped together before the average is calculated. In the output, HR has an average of 52,500, IT has 60,000, and sales has 50,000. Second example. This time, we want to find departments that have more than one employee. We use count to count the number of rows in each department. The having count task greater than one clause filters the group results, keeping only departments where the count is greater than 1. Remember, having works on grouped data, while where works on individual rows before grouping. In the output, HR shows 2 employees, IT shows 2, and sales is excluded because it only has 1. Third example. Here, we group by 2 columns, department and salary. Grouping by multiple columns means each group is formed from rows where both values match. For example, HR with a salary of 50,000 is one group, and HR with a salary of 55,000 is another. We use count again to see how many rows are in each group. In the output, every group shows 1 employee, meaning there are no duplicates with both the same department and salary. Aggregate functions. Aggregate functions let you perform calculations across multiple rows and return a single result. Count is used to count rows. Count star counts all rows, while count column counts only non-null values in that column. Sum adds up all numeric values in a column. AVG calculates the average of numeric values. Min returns the smallest value, and max returns the largest. These functions are often used with group by to summarize data for each group, but they can also be used without grouping to summarize an entire table. Remember, except for count star, aggregate functions ignore null values, so missing data will not be part of the calculation. First example, we use count exclamation to count all rows in the employees table. This returns 5, meaning there are 5 records in total, regardless of whether any column values are null. Second example, we use sum salary to add up all salaries in the table. The result is 279,000, which is the combined payroll for all employees. Third example, we use average salary to calculate the average salary. The result is 55,800, which is the mean value of all salaries in the table. Fourth example, we use min salary to find the lowest salary, which is 50,000, and max salary to find the highest salary, which is 62,000. Fifth example, we combine aggregate functions with group by department. This groups employees by department first, then calculates totals and averages for each group. For example, Sales has 2 employees, a total salary of $105,000, an average salary of $52,500, a minimum salary of $50,000, and a maximum salary of $55,000. IT has similar calculations with slightly higher salaries, and HR has only 1 employee, so all the values match that single salary. Filtering groups versus filtering rows. When working with aggregated data, it's important to understand the difference between filtering rows and filtering groups. The where clause filters individual rows before any grouping or aggregation happens. This is used for raw, row-level conditions. The having clause filters the results of group by after aggregate functions have been calculated. This is used for conditions that depend on aggregated values, such as totals or averages. You can use both where and having in the same query. Where will narrow down the dataset before grouping, and having will then remove any groups that do not meet your aggregated conditions. Remember, if you try to use an aggregate function in where, it will cause an error because aggregation happens after where is applied. First example, we want the average salary per department, but only for employees earning more than $51,000. The where clause removes any employees below that salary before grouping. After filtering, sales has only the $55,000 salary left. IT keeps both its employees, and HR keeps only the $52,000 salary. The averages are then calculated based on this reduced dataset. Second example, we calculate the average salary for each department without any row filtering, then use having to keep only those departments whose average salary is greater than $55,000. This means the grouping is done first, averages are calculated, and then only IT remains because its average salary is $61,000. Third example, we combine both approaches. The where clause first removes all rows where salary is $51,000 or less. Then group by is applied, and finally having removes any groups whose average salary is not above $55,000. The result is again just the IT department. Joining multiple tables. Understanding foreign keys. In relational databases, a foreign key is a column or a set of columns in one table that refers to the primary key in another table. It creates a link between two tables, allowing related data to be connected in a structured way. Foreign keys are crucial because they enforce referential integrity. This means that a foreign key value must match an existing value in the related table's primary key column, or it must be null if allowed. Invalid references are not permitted. This relationship is what makes joins possible, allowing us to combine rows from different tables based on their related keys. Foreign keys can reference a single column, which is most common, or a combination of multiple columns when uniqueness depends on more than one field. We start by creating a table called departments with two columns, department ID, which is the primary key, and department name. The primary key ensures that each department has a unique identifier. Next, we create the employees table. It has employee ID as the primary key, along with first name and last name. The important part here is the department ID column, which is defined as a foreign key referencing the department ID column in the departments table. This ensures that every employee must belong to an existing department unless the column is allowed to be null. We insert 3 departments, sales, IT, and HR. Then we insert 4 employees, each assigned a department ID that matches one of the existing departments. If we tried to insert an employee with a department ID of 4, which doesn't exist in departments, the database would reject the insert. Finally, we run a query that joins the employees table with the departments table on their department ID columns. The result shows each employee along with the name of their department. John Smith is in sales, Jane Doe and Emily Clark are in IT, and Mark Brown is in HR. Inner join. An inner join returns rows from two tables only when there is a match based on a condition you defined. The join condition is usually that a foreign key in one table matches the primary key in another table. Rows that don't have a match in both tables are excluded from the result set. This is the most common join type, and it's typically used when you only want to see data that exists in both tables. To create the join, you use the on keyword, followed by the condition that defines how the rows should be matched. In this example, we select 4 columns: the employee ID, first name, last name, and department name. The query starts with from employees E, which sets E as a short alias for the employees table. We then use inner join departments D to join the departments table, giving it the alias D. The on clause specifies that the join should match rows where E department ID equals D department ID. Because this is an inner join, only employees whose department ID matches a department in the departments table are returned. If an employee had a department ID that did not exist in the departments table, they would not appear in the result. The result shows 4 employees, each with their department name: John Smith in sales, Jane Doe in IT, Mark Brown in HR, and Emily Clark also in IT. Left join, right join, full outer join. When you join tables, you don't always want to see only matching rows. A left join starts with all rows from the left table and includes matching rows from the right table if they exist. If there's no match, the right table's columns will contain null values. A right join is the opposite. It starts with all rows from the right table and adds matching rows from the left table when available. Non-matching left table columns will be null. A full outer join combines both approaches. It returns all rows from both tables, matching where possible, and using null values where no match exists. These joins are helpful for finding data mismatches, spotting orphaned records, or producing complete reports even when some data is missing. We start with the select statement. This tells SQL which columns to display in the results. E.EMployeeID means the employee ID column from the employees table, which we've given the alias E. E.firstname means the first name column from the employees table, also using alias E. D.department name means the department name column from the departments table, which we've given the alias D. Using these short aliases makes the query easier to read, especially if both tables have columns with the same name. The from clause tells SQL which table to start from. Here, we start with the employees table, and we give it the alias E. Next, the left join clause means we keep all rows from the first table, in this case, employees, even if there's no matching row in the second table. The second table is departments, and we give it the alias D. The on condition defines how rows in these tables match. Here, we match rows where the department ID from the employees table equals the department ID from the departments table. This relationship links each employee to their department. When this query runs, it shows every employee. If an employee's department ID matches one in the departments table, we see that department name. If not, the department name is null. For the right join query, the main difference is which table is fully kept. Right join keeps all rows from the table on the right side of the join and fills missing values from the left side with null. For the full outer join query, SQL keeps all rows from both tables, matching where possible and filling in missing values with null on either side. This way, you see every employee and every department, even if they have no match in the other table. Self-joins. A self-join is when we join a table to itself. This is common in hierarchical relationships, like employees reporting to managers, or categories containing subcategories. Because SQL needs to tell the two copies apart, we use aliases. Each copy of the table is treated like a separate table in the join, even though it's really the same table. We can use any join type for self-joins, such as inner join or left join, depending on whether we want all rows or only matching ones. The on condition specifies how rows from the first copy match rows from the second copy. E1 Employee ID. Here, E1 is the first copy of the employee's table. We want to show the employee's unique ID from this copy. E1 First name. This is the employee's first name from the same first copy. E1 Manager ID. This is the ID of the employee's manager stored in the same row as the employee. If the manager ID is null, that means the employee has no manager, like a CEO. E2 First name as manager name. Here, we use the second copy of the employee's table, which we called E2. We take the first name from this second copy because it represents the manager. The as manager name part renames this column in the output so it's clear that it's the manager's name, not another employee. Now, the from employees E1 part. This means we start with the employees table and give it the alias E1. This alias is just a short name so we can refer to it easily. The left join employees E2 means we're joining the employees table to itself. This second copy gets the alias E2. Because it's a left join, all rows from E1, every employee, will appear, even if they don't have a matching row in E2. Finally, the on E1 manager ID equals E2 employee ID part says match each employee's manager ID from the first table with the employee ID from the second table. This way, the second table's row represents the manager of the first table's row. In this way, it lists each employee along with their manager's name using a self-join on the employees table. Cross joins. A cross join takes every row from the first table and combines it with every row from the second table. This is called the Cartesian product. Unlike inner join or left join, there is no on condition. All possible row pairings are created. Cross joins are useful when you need all combinations of two sets, such as pairing each product with each possible size or color. They can also help in testing or generating synthetic data. However, if either table is large, the result can grow very quickly, so use them carefully. We start with select P product name, C color name. Here, P product name means we're taking the product name from the first table, which will alias as P. C color name means we're taking the color name from the second table, which will alias as C. From products P tells SQL that our first table is products, and we're calling it P for short. Cross-join colors C means take every row from the products table and match it with every row from the colors table. The second table is colors, and we're calling it C. Notice there's no on condition here. That's because cross-join doesn't match rows based on a key. It simply creates all possible combinations. In our example, there are 2 products and 3 colors. A cross-join produces 6 rows. Each product is paired with each color, which is perfect if, for example, we're preparing a product catalog for all color variations. Subqueries and set operations. Subqueries in where, select, from. A subquery is simply a query inside another query. Think of it like answering one question by first asking another. We place subqueries inside parentheses, and they can appear in the where clause, the select list, or the from clause. Using subqueries helps break complex problems into smaller, easier-to-solve steps. Depending on where they are used, subqueries can return a single value, a single column, or even a complete table. In this example, you'll see how subqueries work in all three positions: where, select, and from. We start with select first name, salary from employees. That means we want each employee's name and salary. The where salary is greater than the select AVG salary from employees part says, keep only those rows where the salary is greater than the average salary of all employees. The subquery, select AVG salary from employees, calculates the average salary once, and the main query compares each employee's salary to that value. We're looking at a query that lists each employee's first name, their salary, and the average salary of their department. First, the main query is based on the employees table, which we give the alias E so we can refer to it more easily. From this table, we select the employee's first name and their salary. The third column in the output comes from a subquery. This subquery runs separately for each row in the main query. Inside the subquery, we look at the same employees table again, but this time we give it a different alias, E2, to make it clear that it's a separate reference from the main one. The subquery calculates the average salary by scanning all rows in E2, but it doesn't just average every salary. It uses a condition to only consider rows where the department ID in E2 matches the department ID of the employee in the outer query, the one we called E. This means the subquery is correlated. It depends on a value from the outer query. Because of this, for every single employee in the main query, the subquery finds all other employees in the same department, calculates their average salary, and returns that value. Finally, we give that calculated value a label called department average, so in the output table, it's clear what the number represents. In short, each row in the results shows an employee's name, their own salary, and the average salary of the department they belong to. In third query, we write a subquery that selects department ID and the average salary for that department from employees. We group by department ID, so each row in the result represents one department. We give the subquery the alias dep_stats so we can treat it as a table. We then join it with the department's table to replace department IDs with actual department names. This shows how subqueries can act as filters in where, calculated values in select, or entire virtual tables in from. Scalar versus correlated subqueries. In this slide, we are comparing scalar subqueries and correlated subqueries. A scalar subquery is one that always returns a single value. That means just one row and one column. You can place a scalar subquery in a select clause, in a where clause, or even in a having clause, because the database can treat it like a constant value. A correlated subquery works differently. It is linked to the outer query, because it uses columns from that outer query inside the subquery's conditions. This means the correlated subquery runs once for every row in the outer query, and it can give different results for each row. In short, use scalar subqueries when you need a single fixed value, like the highest salary in a company. Use correlated subqueries when you need a calculation that depends on the row you are currently looking at, like comparing an employee's salary to the average salary in their own department. First example, the scalar subquery. The main query looks at all employees and selects their first name and salary. In the where clause, we check if the salary equals the result of the subquery. That subquery runs once and calculates the maximum salary in the entire employees table. Since it's a scalar subquery, it returns exactly one value, in this case, the highest salary in the company. Only the employee or employees with that salary appear in the final results. Second example, the correlated subquery. Here we want to find employees who earn more than the average salary of their own department. We still select first name and salary from the employees table, which we alias as E. In the where clause, we compare salary to the result of another subquery. This subquery calculates the average salary from the employees table again, but this time with a different alias, E2. It has a condition that E2's department ID must match E's department ID from the outer query. Because of this link between inner and outer queries, the subquery runs separately for each employee, using that employee's department to calculate the department's average. If the employee's salary is greater than this average, they are included in the results. In, not in, exists, not exists. In SQL, the keywords in, not in, exists, and not exists are used to filter results based on whether matching rows exist in another set or subquery. The in operator checks if a value matches any value in a list or the results of a subquery. For example, finding all employees whose department ID is in a certain set of department IDs. Not in is the opposite. It returns rows where the value is not in that list or subquery results. However, be careful. If the subquery returns a null, not in might give unexpected results because null is treated as unknown. The exists operator returns true if the subquery returns at least one row. Think of it as asking, does at least one match exist? Not exists is the reverse. It checks if no matching row exists. This is often used for finding records without a related record in another table. Let's go through the examples step by step. In the first query, we select the first name and department ID from the employees table, but only where the department ID is either 1 or 3. The in keyword checks if the department ID value matches any value in the list, here 1 or 3. In the second query, we use not in. This time, we're asking for employees whose department ID is not 1 and not 3. That's why Jane with department 2 and Emily with department 4 are returned. Remember, if the list contains a null, not in may behave unpredictably, so handle nulls carefully. In the third query, we use exists. Here, we want employees who are in a department where the budget is greater than 100,000. The subquery checks the departments table, looking for a department ID that matches the employee's department and has the required budget. Exists returns true as soon as it finds a match. Finally, in the fourth query, we use not exists. We are looking for employees who have no rows in the projects table linked to their employee ID. If the subquery returns nothing, not exists is true, and the employee is included in the results. This combination of in, not in, exists, and not exists is a powerful way to filter data based on related tables or calculated lists. Set operations. Set operations in SQL allow you to combine or compare results from 2 or more queries. The union operator combines the results of 2 queries into a single list, but it automatically removes duplicate rows. If you want to keep duplicates, use union all instead. The INTERSECT operator returns only the rows that appear in both queries. You can think of it as finding the overlap between 2 datasets. The except operator returns rows from the first query that do not appear in the second query. It's useful when you want to find items present in one dataset but missing from another. For all set operations, the 2 queries must return the same number of columns, and those columns must have compatible data types. In the first example, we use union to combine all first names from both the employees and contractors tables. Since union automatically removes duplicates, John and Emily, which appear in both tables, show up only once in the result. In the second example, we use union all instead. This keeps duplicates. That's why John appears twice, once from the employees table and once from the contractors table, and the same goes for Emily. In the third example, we use INTERSECT. This returns only the names that appear in both tables. Here, John and Emily are in both employees and contractors, so they are the only results. Finally, in the fourth example, we use except. This returns names that are in the employees table but not in the contractors table. In this case, Mark and Jane are employees but not contractors, so they appear in the output. Remember, for union, intersect, and except to work, both queries must select the same number of columns, and those columns must be of compatible types. Data modification and table design. Insert into, update, delete. In SQL, the commands insert into, update, and delete allow us to change the actual data stored in a table. The insert into command adds new rows to a table. You can specify values for all columns or just some of them, as long as the required columns are filled. The update command changes data in existing rows. You can update one or multiple columns at once. It's important to use a where clause so you don't accidentally update every row in the table. The delete command removes rows. Again, using a where clause is critical to avoid deleting all rows by mistake. These commands directly modify the data, so they are more powerful and more dangerous than select queries. Let's walk through each example step by step. In the first example, we use insert into employees, followed by the list of columns we want to fill. Employee ID, first name, and salary. Then, inside values, we provide the matching values for each column. Here we insert a new employee with ID 3, name Mark, and salary $55,000. After running this statement, the table now has 3 rows instead of 2. In the second example, we use update employees to change data in the table. The set salary equals $65,000 part tells SQL to change the salary value to $65,000. The where first name equals Jane condition ensures that only Jane's row is updated. Without the where clause, every employee's salary would have been changed. In the third example, we use delete from employees to remove rows. The where first name equals Mark condition means only the row where the first name is Mark will be deleted. After this, the table goes back to having just John and Jane. The main safety tip to remember is, when using update or delete, always include a where clause unless you are absolutely sure you want to affect all rows in the table. Create table, alter table, drop table. In SQL, create table is used to make a brand new table in the database. You define the table name, each column name, and the data type for each column. This is how you decide what kind of data the table can store. Alter table allows you to modify an existing table structure. You can add new columns, remove columns, rename them, or change their data types without losing existing data. Drop table completely deletes a table and all its data from the database. Once dropped, the data cannot be recovered unless you have a backup. This command should be used with caution. These commands are part of data definition language, meaning they change the structure of the database, not just the data inside it. Let's go step by step. First, we use create table departments to make a new table called departments. Inside the parentheses, we define each column. Department ID int primary key means we have a column named Department ID that stores whole numbers and is the primary key, meaning it uniquely identifies each row. Department name text not null means we have a column for the department's name, stored as text, and it cannot be empty. After running this command, the table exists but is empty, waiting for data. Next, we use alter table departments to change the table structure. The add column location text part means we are adding a new column called location that will store text values, like the city or building name. Now the table has 3 columns instead of 2. Finally, we use drop table departments. This command removes the table and all its data from the database completely. After running it, the table no longer exists, so you cannot insert or query it unless you recreate it. This is a destructive action, so it's usually done only when you're sure you don't need the table anymore. Data types. In SQL, every column in a table has a data type, which tells the database what kind of values can be stored there. This prevents invalid data from being inserted and helps the database store information efficiently. INT is used for storing whole numbers, like an ID or quantity. Text stores character data, like names or descriptions. Date stores calendar dates in a year, month, day format. Boolean stores only true or false values. Often used for yes or no decisions. Choosing the correct data type is important because it ensures accuracy and can make your queries run faster. If you choose a type that's too general, you might store incorrect data, and if you choose one that's too strict, you might reject useful data. In this example, we start by creating a table called products. The first column, product ID int primary key, means it stores whole numbers, and each value must be unique. This is perfect for IDs. The second column, product name text not null, stores words or sentences such as the product's name, and it cannot be left empty. The third column, release date date, is meant for storing calendar dates in year, month, day format. This lets you sort and filter by time easily. The fourth column, in stock Boolean, is a true or false field. True means the product is available, and false means it's not. Next, we insert one row. Product ID 1, named laptop, released on August 1st, 2025, and marked as in stock. When we run select star from products, the database returns all rows and columns. In our example, we see the product ID, name, release date, and that the stock status is true. Constraints. Constraints in SQL are rules that make sure your data stays accurate and consistent. A primary key is a column or group of columns that uniquely identifies each row in a table. No two rows can share the same value here. A foreign key is a column that points to the primary key in another table, creating a link between the two tables. A unique constraint means all values in that column must be different, but unlike primary key, it can still allow one null value unless you also add not null. A not null constraint means you must always enter a value for that column. You can't leave it empty. A default constraint assigns a value automatically if you don't provide one when inserting data. We begin by creating a table called departments. The first column, dept ID int primary key, is an integer that uniquely identifies each department. No two departments can have the same ID. The second column, dept name text unique not null, stores the department's name. It must be unique across the table and cannot be left empty. Next, we create the employees table. The empID int primary key ensures each employee has a unique ID. The emp name text not null means the employee's name must always be provided. The dept ID int column stores the department ID this employee belongs to. The join date default current date automatically assigns today's date if no join date is specified. Finally, we define foreign key. Dept ID references department's dept ID. This means any value in employee's dept ID must already exist in department's dept ID, ensuring valid links between the two tables. We then insert one row into departments, department ID 1 named IT. Next, we insert an employee with ID 101, name Alice, in department 1. We leave join date empty, so the default today's date is used. When we run the select query, we see the employee ID, name, department ID, and the join date automatically filled in as today's date. Advanced SQL for real-world use. Window functions. Window functions in SQL let you perform calculations across a set of rows related to the current row, without grouping or collapsing results like group by does. Row number gives each row a unique sequential number, starting from 1 within each partition you define. Rank is similar, but if two rows are tied, they get the same rank, and the next rank number is skipped. Lead lets you look forward to see a value from a later row, while lag looks backward to see a value from a previous row. All these functions use the over clause to define the window, which rows to consider, and in what order. In this example, we start with a table of employees showing their names, department IDs, and salaries. In our query, we select the employee's name, department ID, and salary. Then, row number over partition by dept ID, order by salary, DESC, gives each employee a unique row number within their department, ordered from the highest to the lowest salary. For example, in Department 10, Bob gets row number 1, Charlie gets row number 2, and Alice gets row number 3. Rank over partition by dept ID, order by salary, DESC, works similarly, but it assigns the same rank to rows with equal salary. In Department 10, Bob and Charlie both own 7,000, so they both get rank 1, and Alice jumps to rank 3. Lag, salary, over partition by department, order by salary, DESC, looks at the previous row's salary within the same department. Bob has no previous row, so it shows null. Charlie's previous salary is Bob's 7,000, and Alice's previous salary is also 7,000. Lead salary over partition by department, order by salary, DESC, looks at the next row's salary in the same department. Bob's next salary is Charlie's 7,000. Charlie's next salary is Alice's 6,000, and Alice has no next row, so it's null. The over clause in each function tells SQL to reset calculations for each department and order rows by salary in descending order. The case statement. The case statement in SQL allows you to add conditional logic directly into your queries. You can think of it as the SQL version of if-else in programming languages. It works by checking conditions in order. When a condition is true, SQL returns the result you specify and stops checking further conditions. If none of the conditions are true, the else part runs to provide a default value. Case is often used to categorize data, create labels for groups, or transforming raw values into something more meaningful in query results. We begin with a table of employees showing their names and salaries. In our query, we select the employee's name and salary, and then use a case expression to classify their salary level. The first condition checks if the salary is greater than or equal to 7,000. If that's true, it returns the word high. This covers both Bob, with a salary of 7,000, and Diana, with 8,000. If the first condition isn't met, the second condition checks if the salary is greater than or equal to 5,000. If that's true, it returns medium. This applies to Alice, who earns 6,000. Finally, if neither of the first two conditions is true, the else part runs and returns low. That's the case for Charlie, whose salary is 4,500. The result is a categorized view of salary data, making it easier to read and analyze. Common table expressions. A common table expression, or CTE, is like creating a temporary table that only exists for the duration of your query. You start by writing with, followed by a name for your CTE, and then defining it with a select statement. The main query that follows can use the CTE as if it were a real table. This makes long and complex queries much easier to read and maintain. Since you can break them into logical steps, CTEs are also reusable within the same query. You can reference them multiple times without rewriting the same subquery. We begin with a table called sales. which has order IDs, customer IDs, and purchase amounts. The first part of our query starts with the with keyword, which signals that we're defining a CTE. We name this CTE customer totals. Inside the CTE, we select the customer ID and use the sum function to calculate the total amount each customer has spent. We group the results by customer ID so that each row in the CTE represents one customer. After defining the CTE, our main query selects customer ID and total spent from this temporary result set. We also add a where condition to only show customers whose total spending is greater than 250. In the example output, customer 101 appears with a total of 500 because they had two orders, one for 200 and another for 300. Customer 103 appears with a total of 400 from a single order. Customer 102 is excluded because their total spending was only 150. This approach keeps our logic clean and avoids repeating the same aggregation in multiple places. Views. Create view. A view is like a shortcut to a query you use often. Instead of rewriting the same complex query every time, you can save it as a view. Think of a view as a virtual table. It doesn't store its own data. It always pulls the latest results from the underlying tables whenever you use it. You create a view with the create view command, give it a name, and then define the query you want it to store. After that, you can treat the view like any other table in your select statements. This makes your code shorter, cleaner, and easier to maintain. We start with the sales table, which lists order IDs, customer IDs, and amounts spent. The create view command is used to define a new view called high spenders. Inside this view, we select each customer ID and use sum amount to calculate the total amount they've spent. We group the results by customer ID so that each customer has a single total. The having clause filters the results to only include customers whose total spending is greater than 250. Once this view is created, we can use select star from high spenders, just like we would query a normal table. The benefit is that we don't have to rewrite the sum and group by logic every time. The view always pulls fresh data from the sales table, so if the table changes, the view's results update automatically. In our example output, customer 101 spent a total of 500, and customer 103 spent 400, both above our threshold. Indexes and performance basics. An index in a database works just like the index at the back of a book. If you need to find a specific topic in a large book, you don't flip through every page. You use the index to jump straight to the right spot. In the same way, a database index helps the system find rows much faster without scanning the entire table. However, indexes are not free. While they make searches and select queries faster, they can slow down insert, update, and delete operations because the index also has to be updated every time the data changes. Good practice is to add indexes on columns you search or filter by often, but avoid adding too many or your write operations may become slower. We have an employees table with employee IDs, first and last names, and department IDs. To make lookups by last name faster, we create an index using create index IDX last name on employee's last name. Here's what's happening. Create index tells the database we want to make a new index. IDX last name is simply the name we're giving to the index. This name can be anything meaningful to you. On employee's last name means create the index on the last name column in the employees table. Once this index exists, when we run select star from employees where last name equals Smith, the database doesn't need to check every row one by one. It uses the index to jump straight to the matching rows, just like flipping directly to the right page in a book. Without the index, the database would scan the whole table, even if only one row matches. With the index, it can find results much faster. The trade-off is that when we insert, update, or delete a row, the index also needs to be updated, which takes extra time. That's why we add indexes carefully, only where they will really speed up common queries. SQL in the workplace. Writing queries for reporting and dashboards. When you write SQL queries for reports or dashboards, the goal is not just to retrieve data, it's to summarize it in a way that answers specific business questions. Dashboards usually show aggregated data, meaning numbers are grouped and calculated, such as total sales by month or the number of new customers per region. The group by clause lets you split your data into categories, while aggregate functions like sum, count, and AVG calculate totals, counts, or averages within each group. The where clause filters rows before grouping, while the having clause filters groups after aggregation. Finally, formatting the output, like adding aliases for columns or ordering results, makes your results dashboard-friendly and easy to read. Our sales table contains a sale ID, the date of the sale, the region where it happened, and the amount. In the first query, select region, sum amount as total sales, tells the database we want to display each region and the total of the amount column for that region. Sum amount adds up all amounts for that region. As total sales is an alias, it changes the column's output name so it's easier to read. The from sales part says we are using the sales table. Group by region means group the rows together based on the value in the region column, so all north sales are grouped, all south sales are grouped, and so on. The output shows each region with its corresponding total sales amount. In the second query, we added having sum amount greater 1,000. This tells the database, after grouping, only keep the regions where the sum of the amounts is greater than 1,000. The difference between where and having is important. Where filters before grouping. Having filters after the aggregation has been done. This kind of query is exactly the type you'd use to build dashboard widgets showing top-performing regions or products. Connecting SQL with tools. SQL isn't just for running queries in a database console. It's also the foundation for many business tools. In Excel, you can connect directly to a database by using the Get Data option under the Data tab, then choosing From Database. This allows you to pull query results straight into a spreadsheet, refresh them, and use Excel's charts and pivot tables for reporting. In Power BI, you connect by selecting the database type, entering credentials, and either importing the entire table or writing a custom SQL query. This lets your dashboards update automatically when the database changes. With Python, you can use built-in or third-party libraries like SQLite 3, SQL Alchemy, or pandas.readsql to run queries and work with the results as data frames, making it easy to analyze and visualize data programmatically. These connections allow you to automate reports, keep dashboards live, and ensure your data-driven decisions are based on the most recent information. We start by importing SQLite 3 to handle the database connection, and pandas for working with the results. First, SQLite 3.connect company.db opens a connection to a SQLite database file called company.db. This is like logging into your database so we can run queries. Next, we store a SQL query in a variable named query. The query selects the department, calculates the total salary for that department using sum salary, and groups the results by department. Then we use pd.readsql query con to run the query and directly load the results into a data frame. A data frame is like a table in memory that you can easily manipulate or plot. After that, we close the database connection using con.close. a good habit to prevent unused connections from staying open. Finally, printdf shows the results. In this example, each department is listed alongside its total salary budget. This exact query could be connected to Excel or Power BI instead of Python, if you prefer a no-code solution. Working with company databases. In the workplace, you'll rarely work with just one database type. Different companies use different systems based on their needs. PostgreSQL is a powerful open-source database, often chosen for analytics-heavy projects and modern applications. It supports advanced SQL features and is widely used in startups and data science teams. MySQL is one of the most common databases for web applications, especially in combination with PHP, WordPress, or e-commerce platforms. SQL Server, developed by Microsoft, is widely used in corporate environments. It integrates smoothly with Excel, Power BI, and other Microsoft tools, making it a go-to choice for internal reporting. Oracle Database is designed for large-scale enterprise applications with heavy transaction loads. It's often found in finance, telecommunications, and government systems. Although the SQL language is mostly the same, each system has slightly different connection methods, default settings, and extra features. Your main job is to understand how to authenticate, connect, and then run queries efficiently in whichever system your company uses. We begin by importing pandas for handling query results and SQL Alchemy for creating database connections. First, we connect to PostgreSQL. The connection string starts with PostgreSQL plus psycopg2, followed by your username, password, host address, port, and database name. We then run a simple select query to get the first 5 employees. Second, we connect to MySQL. The process is similar, but the connection string uses MySQL PyMySQL. Again, we fetch the first 5 employee records. Third, for SQL Server, we use MSSQL plus PyODBC with a driver specification like ODBC driver 17 for SQL Server. This lets Python talk to SQL Server using Microsoft's ODBC driver. Finally, for Oracle, we use Oracle plus CX Oracle and include the service name. Since Oracle uses roundnum instead of limit, we use where roundnum equals 5 to fetch the first few rows. In each case, pd.readsql runs the query and stores the results in a data frame, making them easy to view or analyze. This approach means that once you know the connection details for your company's database, you can plug them into the same Python workflow, no matter which database system it is. Query optimization basics. In this slide, we will learn what query optimization means and why it is important for software development jobs. Query optimization is the process of making your SQL queries run faster and use fewer resources. This is important because slow queries can make applications slow and increase server costs. Common causes of slow queries include scanning large tables, missing indexes, and inefficient joins. Indexes help the database find data quickly, just like a book's index helps you find a topic without reading every page. To avoid unnecessary data scans, write queries that filter data early, using conditions in where clauses. You can also use the explain command to see how the database executes your query. This helps identify slow parts and improve them. In this slide, we will look at some examples of slow SQL queries. These examples show common patterns that cause slow performance in real-world applications. First, using select star, which means selecting all columns, especially without a where clause, causes the database to read entire tables. This wastes time and resources. Second, missing indexes on columns used in joins forces the database to scan whole tables to combine data, making joins slow. Third, using select distinct when not needed causes extra processing to remove duplicates, slowing the query down. Lastly, using subqueries in places where joins could be used often results in slower queries because the database has to run multiple smaller queries. On the next slide, we will see how to improve these slow queries and make them efficient. Now let's see how to improve those slow queries. First, always select only the columns you need and use where clauses to filter rows. This reduces data scanned and sent back. Second, create indexes on columns used for joins and filters. Indexes speed up lookups and joins significantly. Third, remove distinct if it is not required. Sometimes data is already unique, so distinct wastes processing power. Fourth, replace subqueries with join operations when possible. Joins are often faster and easier for the database optimizer to handle. By applying these simple changes, you can greatly improve query performance and make your applications faster and more scalable. Here are some slow query examples and their improvements. First, selecting all columns without a filter scans the entire table. Instead, select only needed columns and filter rows using where. Second, if you join tables on columns without indexes, the join becomes slow. Create an index on those columns to speed it up. Here, IDX customer ID is the name of the index. On orders specifies the table on which the index will be created. In this case, it's the orders table. Customer ID is the specific column or columns in the orders table that the index will be built on. This means the database will create a separate, sorted list of all the customer ID values. Third, using distinct when the data is already unique wastes resources. Avoid it if you know the data has no duplicates. Fourth, subqueries can be slow. Replacing them with joins usually improves performance by letting the database optimize better. These changes make queries faster and your application more responsive. Security and permissions. Database security is crucial to protect sensitive data and ensure only authorized users can access or change information. Permissions are rules that define what actions users can perform on database objects like tables and views. The grant command is used to give specific permissions to users or roles. For example, you can allow a user to select data or insert new rows. The revoke command removes permissions previously granted, limiting what a user can do. Common permissions include select to read data, insert to add new data, update to change existing data, and delete to remove data. You can grant permissions to individual users or to roles, which are groups of users. Using roles makes managing permissions easier for many users. Properly managing permissions keeps your database safe and helps comply with security policies. Here are examples of grant and revoke commands. The first command gives user John permission to read data with select and add data with insert on the employees table. The second command removes the insert permission from John, so he can no longer add data but can still read it. The third command grants all privileges on the company database to a role named admin role. Roles help manage permissions for many users at once. Using grant and revoke helps you control who can do what in your database, which is essential for security and data integrity. Version control of SQL scripts. In this slide, we will learn about version control for SQL scripts using Git. Version control is essential in software development. It helps keep track of changes made to your SQL files, so you can see who changed what, when, and why. Git is a popular version control system that works well with any text files, including SQL scripts. Basic Git commands you should know include clone to copy a repository to your local machine, add to stage changes, commit to save changes with a message, push to upload your changes to a remote server, and pull to get the latest updates from others. Organizing your SQL scripts in Git repositories allows you to keep them structured and accessible. Using Git also makes collaboration easier because multiple developers can work on the same scripts without overwriting each other's work. Version control gives you history of your work, allows you to roll back to previous versions, and improves teamwork and code quality. SQL scripts. SQL scripts are essential in software development. SQL scripts are text files that contain one or more SQL statements. Instead of running single queries one by one, scripts allow you to run multiple commands together in sequence. Scripts usually have a .sql file extension. You can write and save scripts using any text editor or database tool. You can run scripts directly in database management tools like MySQL Workbench or through command line interfaces using commands like MySQL or PSQL. Using scripts helps automate repetitive tasks such as creating tables, inserting initial data, or running complex updates. Best practices for writing scripts include adding comments to explain sections, formatting code clearly for readability, and breaking large scripts into smaller, reusable parts. Scripts improve efficiency, reduce errors, and help you manage database changes in a controlled way. Here is a sample SQL script. First, it creates a customers table with 4 columns: customer ID, customer name, email, and created at with a default date. Next, it inserts 2 rows of sample customer data. Finally, it updates the email address for the customer with ID 1. Comments at the top of each section help explain what the code does. Writing scripts like this lets you run multiple commands at once and automate database setup and updates.
Thanks for watching.